Now, in this first part of our example here, we need to determine all the possible zeros of the polynomial or roots. Zeros, in fact, mean roots of the polynomial. So, over here, in order to determine all the possible rational roots of the polynomial, first we start by considering the constant term in the polynomial as c and the leading coefficient of the polynomial as a. And then we start by listing all the factors, all the possible factors of c and a. So I start with the factors of c, then the factors of a, which are, for c is 15, then all its possible factors are 1 and 15, or 3 and 5. So c is in fact plus or minus 1, plus or minus 3, plus or minus 5, and plus or minus 15. They're plus or minus because in fact they're rational. They could either be positive or negative. And then for the factors of a is prime, it's 2, so the only factors of a are 1 and 2, so it's plus or minus 1 and plus or minus 2. Now the possible rational zeros of the polynomial are in fact the set consisting of c over a. So it's all the factors of c divided by all the factors of a. So all the factors of c divided by 1 are in fact all the factors of c, plus or minus 1, plus or minus 3, and plus or minus 15. Then all the factors of c divided by the second factor of a, which is 2, we end up with plus or minus half, plus or minus 3 over 2, plus or minus 5 over 2, and plus or minus 15 over 2. So c over a contains all the possible rational roots of the polynomial. Now, it doesn't mean that they're all zeros of the polynomial. Know that this is a polynomial of degree 3, so it admits at most 3 roots. So they can't possibly all be zeros of the polynomial. But if the polynomial would admit a rational zero, in that case it will be among the set c over a. Now before we move to part 2 of the example, let's just discuss a bit why is it that the possible rational zeros of the polynomial are in fact among the set c over a. Now if we take an example of a quadratic equation that is factored into two linear factors. So, for example, if we consider a polynomial which has two linear factors. So, over here, if we were to expand this polynomial, the leading term would be mbx squared, and then we expand and simplify the rest, and the constant would be n times d. Now, if we look at the zeros of this polynomial, for the first factor it's negative n over m, and for the second one it's negative d over b. Now, if we look at c and a of this polynomial, you'd notice that the first root, negative n over m, has its numerator at c as a factor of c and its denominator as a factor of a. So n over m is part of the set c over a. Similarly, for negative d over b, you notice that its numerator is a factor of c and its denominator is a factor of a. Then the second root is also part of the set c over a. And this is why if any rational zeros of the polynomial exist, they would be among the set c over a. Now, if we move to part 2, how could we actually use the set c over a in order to factorize the polynomial completely and find all its roots? Now, as we know, since they're possible zeros, then we start trying them one by one. When we get to a 0, it should make the polynomial equal to 0, which means that over here, when we start trying them, f of 1, for example, if you replace f of x by 1, f of 1 is not 0. Therefore, x equal to 1 is not a 0 of the polynomial. So we move on. We start by trying f of negative 1. Then f of negative 1 is also different than 0. Then negative 1 is not a root of the polynomial, so we move on. We keep on trying them until we reach a 0 of the polynomial. Now, in this case, negative 3 over 2 would be our 0, which in fact it will be the only possible the only rational root of the polynomial. So over here, since we have f of negative 3 over 2, so that's for part 2, f of negative 3 over 2 equal to 0, then x equal to negative 3 over 2 is a root of, or a 0 of f of x. Since it's a 0, then 2x plus 3 is a factor of the polynomial. Now, over here, since we already found a 0 or a factor of the polynomial, we can divide. To start factorizing, we can start dividing the polynomial by that factor. You could use long division and divide f of x by 2x plus 3, or use synthetic division and divide by negative 3 over 2, so which we will use here. So over here, if we list in decreasing order the coefficients of the polynomial, and then we have our root here. So synthetic division, we drop the first coefficient, then 2 times negative 3 over 2 is negative 3. Their sum is negative 14. Then negative 14 times negative 3 over 2 is 21. 21 minus 11, that's a 10. 10 multiplied by negative 3 over 2, that's a negative 15. And I remind you here that the remainder of the division must be a 0, or else you did not find a correct 0 of the polynomial. Negative 3 over 2 wouldn't be a 0. So if you ever divided by a 0 of the polynomial and you did not end up with a remainder equal to 0, in that case, you either did something wrong with the division, or negative 3 over 2 is not a 0 of the polynomial in the first place. So you revisit the work. So then f of x can be written as x plus 3 over 2 into 2x squared minus 14x plus 10. Of course, I want 2x plus 3 to be the factor of the polynomial, since, as you can see here, the leading coefficient of the polynomial is a 2 and is not a 1. So over here, we factor out a 2 from this factor, and then multiply the first factor by that 2. So we would end up with 2x plus 3 into x squared minus 7x plus 5. So now we wrote f of x as a product of a linear factor with a quadratic. Of course, for the quadratic factor to keep on factorizing it and finding its roots eventually, we could also use the method of possible rational roots, but in fact, since this is quadratic, we can use the quadratic formula in order to find the roots of the polynomial of this polynomial and factorize it. So over here, delta is 7 squared, which is 49, minus 4 into 5, which is 20. So delta is 29. Then x is 7 plus or minus square root of 29 over 2. So as you can see here, that the other two zeros of the polynomial are irrational. They're not rational. This is why we did not really find them in the set C over A. So to factorize f of x completely, fx would be 2x plus 3 into x minus 7 minus square root of 9 over 2 to x plus 7 plus square root of 29 over 2. So these are the three factors of the polynomial. Therefore, to solve f of x equal to 0, f of x is 0 when each of these three factors is 0, then x would be negative 3 over 2, or 7 minus square root of 9 over 2, or x is 7 plus square root of 29 over 2. So these are the 3 zeros of the polynomial f of x. Now, before we move on, I just have a quick remark. In case you tried all the possible rational roots of the polynomial, which are the elements of the set C over A, and none of them worked, none of them set the polynomial equal to 0. So in that case, it doesn't mean that the polynomial has no real roots. In that case, it would mean that the polynomial does not have any rational roots. So the roots of the polynomial could either be irrational, or the polynomial could not have any irrational roots. In these cases, we would actually use our GDC in order to determine if the polynomial admits irrational roots or not.